we are diving into a core data structure concept, depth-first traversal, also known as depth-first search. This method explores a graph by going as deep as possible before backtracking. And of course, we will implement it in Java. Let's get started. DFS, a search algorithm for traversing a tree or graph data structure. Alright everybody, depth-first traversal is a search algorithm for traversing a tree or graph data structure. We can break this down into 3 steps. When navigating a graph, we will pick a route and we will keep on going until we reach a dead end or a previous visited node. If we do, then we will move on to step 3. We will backtrack to the last node that has unvisited adjacent neighbors. First one, pick a route. Second one, keep going until you reach a dead end or a previously visited node. Third one, backtrack to last node that has unvisited adjacent neighbors. Let's navigate this maze using a depth-first traversal approach. Here's the entrance and here's the exit. So, the general concept of depth-first traversal is that when we reach more than one adjacent neighbor, we are just going to pick a route. Let's say we prefer right turns over left turns, but you can really set any rule that you want when faced with more than one adjacent neighbor. I am just going to pick out and keep on going. And if we reach a dead end, then we are just going to backtrack to a node that has some unvisited adjacent neighbors. So there's no more place we can go. So we are going to backtrack to a node that has some unvisited adjacent neighbors. So there is no more place we can go. So we are going to backtrack all the way back to this insertion. Right here, this route is unvisited. So we will continue going, not backtracking yet. There is no dead backtracking yet. There is no dead ends, but now there is, so we backtrack and keep on going. So this is what this looks like sped up, and we have reached the end. Let's use a depth-first traversal approach to navigate this graph. Maybe we are at node A and we need to travel to I, but we don't know where I is. One way in which we can keep track of our position is to use a stack, or in the case of recursion, we can use a whole stack. Whenever we visit a node, we will push it onto the stack. We can either travel to nodes B or D. So we will mark D as visited and push this node onto the stack. Then we can either go to E or G. Let's go to G. We will push that onto the stack, then it E, and now we circle the round back to D. But D is already marked as visited. So we are going to backtrack to a node that has unvisited adjacent neighbors, which is a so we will pop all of these nodes off of the stack all the way back to a which has unvisited adjacent neighbors. And this time we will go down this route and push all of these nodes onto our stack, and we have reached the end using a depth-first traversal approach. When simplified, you pick a route, you keep going. When you reach a dead end or a node you already visited, you backtrack to a node that has unvisited adjacent neighbors, and you repeat steps 1 through 2. Now that we have seen how depth-first traversal works in graphs, let's shift to binary trees. In trees, depth first traversal is performed using three main traversal types: pre-order, in-order, and post-order. Each follows a different order for visiting nodes. Let's start with pre-order traversal. The idea here is simple. We visit the root node first, then recursively visit the left subtree and finally the right subtree. This is useful when we want to copy a tree or evaluate prefix expressions. Here's the step-by-step algorithm. Visit the root, traverse the left subtree in pre-order, traverse the right subtree in pre-order. That's it, simple and clear. So now look at this example. First go to A and second left side B, D, H, then go to right side I, E, C, F, J, K, G. So this is how pre-order traversal works. Next, in-order traversal. This one is super important for binary search trees. We go left subtree first, then the root, then the right subtree. In a binary search tree, in-order traversal gives us the nodes in sorted order. Here's the in-order algorithm. Traverse the left subtree, visit the root, traverse the right subtree. It used when we want to process nodes in increasing order. Now look at this in-order traversal example. First, go to the left subtree, H, D, I, B, E, A, J, F, K, C, G. So this is how in-order traversal works. Lastly, we have post-order traversal. This time we visit the left subtree, then the right, and finally the root. This is perfect for tasks like delete all nodes or evaluating postfix expressions. So again, the algorithm is traverse the left, traverse the right, visit the root. Just remember the root comes last in post order. Then look at the post order traversal example. First process the left subtree, H, then right subtree and the root, H, I, D, E, B, J, K, F, G, C, and lastly A. And that's it. We have covered how depth first traversal works in graphs and the three depth first based three traversal methods. Alright, well, let's implement this in code now. Alright, well, let's implement this in code now. And here we are people, so I am going to be using a graph that utilizes an adjacency map. If you are using an adjacency list, the code's just going to be a little bit different, but the concept is really still the same. So this is my adjacency matrix now. Within the graph class, we are going to create a depth first traversal method and a helper method. So this will be public void and we will name this depth first search, and there will be one parameter, an index of where we would like to begin. To keep track of the nodes that we have already visited, what some people like to do is that they will create a boolean within their node class such as boolean visited, and they will just mark it as false or true. However, it's very easy to forget to change these back to false when you exit the depth first search. So what I'm going to do instead is create an array of booleans and size will be equal to the length of the matrix. So let's create a boolean array. And I will name this visited equals new boolean, and the size of our array is the length of our matrix. Then lastly, we will implement a helper function. So let's name this DFS helper, and we will pass in our source and our boolean array visited. Then we just need to create to create this method. Private pivot void DFS helper, and there are two parameters. In source, an array of booleans named visitor. You can either implement a depth first search iteratively using a stack, or you can utilize the call stack if you use recursion. In this example, we are going to use recursion. When we invoke this helper function, we are going to check to see if the current node that we are on is visited or not, and we can use an if statement. If our visited array at index of source is equal to true, or you could write the shorthand and say if visited at index of source, this returns a boolean value. If we have already visited this node, we are going to return. Else we will mark this node as visited. Else visited at index of source equals true. If you would like, although these parts not necessary within my console, I am just going to print that visited this node. So within a print line statement, I do have my nodes within an array list. I'm just going to access the data of one of these. Nodes dot get source dot data plus equals visited. This part is not necessary, but it's going to help with my demonstration. Example, maybe we start at node A. We need to find any adjacent neighbors. If we are using an adjacency matrix, we need to iterate over this row. We can use so into I equals 0. We will continue this as long as I is less than the matrix at index of our source. Dot length. This equals the length of a row. Then increment I by 1. We are checking to see if one of these elements is 1. That means an adjacent neighbor that we can travel to. Use statement at indices of our source and I. Source is the row that we are working with, I is the column. If this is equal to 1, then we will invoke the DFS helper method again. So this is recursive. We will pass in I as well as our boolean array name visited. If we successfully search through an entire row outside of the for loop, let's return, and that's it. So let's run this within my main class. I will call the graph's depth first search method and pass in an index of a starting node. So let's begin at 0. We visit A first, B, C, D, E. Let's try B, which has index of 1, B, C, D, E, A, C, which has index of 2, C, D, E, A, B. Okay, now pay attention to this. This is a directed graph. And we are beginning at D. There's no place that we can go, so we are stuck at D. Only visit D. And lastly, have E, which has an index of 4. E, A, B, C, D. Alright everybody, that is the depth first search algorithm. You pick a route, you keep going. If you reach a dead end or an already visited node, backtrack to a previous node with unvisited adjacent neighbor. If you would like a copy of this code, I will post this to the comment section down below. Don't forget to get this video a thumbs up. Also leave a random comment below.